arithmetic hyperbolic 3 manifolds. And I'll give an example for what the theorem comes down to in a very special case. So I will work with a field which is Q adjoint the square root of -1, and I will use n equals 2. So I'm interested somewhere in the group GL2 over this field K. And so in this case, a locally symmetric space. First of all, the symmetric space itself will be 3-dimensional hyperbolic space. And so one model for 3-dimensional hyperbolic space would be the complex numbers times the positive reals. And if you think of these as terms x, y, then the hyperbolic structure, the hyperbolic metric, is given by similar formula as for 2-dimensional hyperbolic space here, just add a variable. And one can check that the group of isometries is isomorphic to PSL2 of the complex numbers. So that's the group of orientation-preserving isometries. And so we can play the same game as for GL2 over Q. So we take inside SL2 of the ring of integers in K a congruent subgroup. And in fact, for some very small technical reasons, I will assume, as I did later on last time, that actually it contains a congruent subgroup of the form gamma 1 of n. So again, these are the matrices which are congruent to a matrix of this form, modulo n. Okay, and then we form this locally symmetric space, which is H3 mod gamma. And so these spaces were first studied, so these are called Bianchi manifolds. So they were introduced in 1892 by the differential geometry Luigi Bianchi. So they're very classical objects, in fact. And in fact, I should say that if gamma is too large, they are not actually manifolds, but only orbifolds, maybe canonically. But if gamma is sufficiently small, they are really manifolds. So they're hyperbolic 3 manifolds. And so let me try to draw a picture. And in fact, the picture will look quite similar to the picture for the modular curve. So this time, somewhere on the bottom, you have the complex numbers, and then over it, you have hyperbolic 3 space. And then inside there, inside the complex numbers, you have this lattice given by this ring of integers. And so you will have somewhere 0, somewhere 1, somewhere I, and somewhere 1 plus I. So you have this. And so I can now again try to draw a fundamental domain. And so this time I will take straight lines above it. And then last time I drew these circles where the other boundary. And so this time, these circles will become half spheres. Above, around all of these 4 points. Also here, I'm not good at drawing that. And so you see that some of the picture also looks pretty similar to the case of the modular curve. So fundamental domain would somehow be the interior of this cone which goes off to infinity, and then here it will have some spheres, parts of spheres which bound it. That's the fundamental domain. So this is in the case that gamma is the full congruence, the full group SL2. Okay, and so I wanted to make several remarks in which situation is very different from the case of the modular curve we looked at last time. So first of all, for obvious reasons, there's no complex structure on this guy. Simply for the reason that it's of odd dimension, so there's no chance. And so a fortiori, there can be no algebraic structure. So these are really just hyperbolic 3 manifolds. And another remark is that in this case there's lots of torsion. So I wrote down one example. So if gamma is a congruent subgroup gamma naught, which just means it just has a 0 mod p for some prime p, where p is a prime whose norm is 4969, I think. So it's not all too big, but it turns out in this case a certain 13-digit prime will divide the order of the torsion subgroup. It takes the first integral homology, look at its torsion subgroup, and then there will be huge sporadic primes which divide this. And so it is expected. No, of course not me. So I took this example from the work of Sengun. It is expected that the order of the torsion subgroup grows exponentially with the volume of this hyperbolic 3 manifold, and in many slight variations of the setup, this is actually a theorem. So, for example, there is a theorem of Bergeron-Venkatesh, which works in a slight variation of the setup where this hyperbolic 3 manifold would be compact. And maybe they also introduce some coefficient systems. But and also there's an Iwasawa theoretic argument which produces lots of torsion. So it's known that there's a lot of torsion, but apart from that, very little is known about this torsion. So one knows that it's there. There's a whole lot of it, but that was mostly what one knew. Nonetheless, the following theorem was expected to be true for a long time. So the rough form is the following. So assume that the mod P homology is non-zero for some group gamma. I mean, it's a very weak form, which is probably trivial in the way I stated it, but I will refine it so that there's really content to it. There exists some Galois representation of the absolute Galois group of this imaginary quadratic field going to GL2 FP bar, which is unramified outside this level n where I choose my n is there. Right. With certain properties that I'm about to explain. So that such a result could be true was expected since, I guess, the 1970s. So there were examples of Fritz Grunewald, which somehow gave numerical evidence that if there is such a torsion class in the homology, then there is some Galois representation which seems to be attached to it in some sense. And I guess a precise conjecture because this is GL2. So in general, there's a locally symmetric space for GLN on which some of GLN would act. And you would divide by a congruent subgroup of GLN of this thing, and then you would expect representations into GLN. But I mean, at this point, it's totally mysterious because this picture on these black spots doesn't have anything to do with Galois representations. It's just real topology. Yeah. I mean, at this point, you could just take the trivial representation and you'd be fine. I mean. So a precise conjecture which was put forward, for example, by Asch in 1990. So for a more precise formulation, I have to talk about Heck operators. And it is because, so it's really crucial that I work with congruent subgroups here, and some of the way this congruence property is used is that it's possible to define Heck operators. So how does this work? So fix some prime ideal in this ring of integers, not dividing n, prime ideal. And I carefully chose an imaginary quadratic field for which all of these are principal, so it's generated by some element in the ring of integers. And then I can look at the following subgroup. So I intersect my congruent subgroup gamma with a certain conjugate of it. And then I can look at the following correspondence between the arithmetic manifold I'm interested in, and it will again go towards it, and in between you take a finite cover. So this first projection is just the obvious projection because this is a subgroup of gamma, and for the other projection you first identify this with the quotient by a conjugate subgroup. And then this conjugate subgroup, gamma will be, again, a subgroup. And so you can now project, again, to this guy. So pi 1 and pi 2 are finite covering maps. And so what you can do with these covering maps is you can define, any correspondence somewhere acts on the homology. What you do is you pull back, and then you push forward, whereas this second map uses that you have a finite covering map, so you can define a push-forward map on homology. So this gives you an endomorphism of this homology group you're interested in. And the fact is that these endomorphisms for p not dividing n commute.
So now the little p is not the residue factor?
Sorry, yes. So this p has nothing to do with this p. I'm sorry. This causes confusion. Right. So this implies that there exists a basis of simultaneous. Well, there exists simultaneous eigenvectors. Yeah, I should really semi-simplify too. I don't say there's a basis of simultaneous eigenvectors, but for but for any system, well, there exists simultaneous eigenvectors, and I will just talk about those which are eigenvectors. Some are good enough. So the more precise form of the theorem is the following. So let alpha be, so these alpha p's are numbers in fp bar, be a system of Hecker eigenvalues. Appearing in such a homology group. So yeah, I go to an algebraic closure to see all of them. Then there exists a representation rho alpha, which goes from the absolute Galois group of K to GL2 FP bar, which has the following property. That if you take the trace of a Frobenius element corresponding to this P, so I should say it's unramified outside N, is given by the Hecker eigenvalue. So it's a Frobenius conjugacy class. This definition I don't really want to recall, but
You don't have to exclude the little Roman p from the outside.
sorry. so yes. Thanks. Hmm? Yes, thank you. Okay, here we are. Suffice to say that by Shimotarov density theorem, these Frobenius elements are dense in the subgroup, so giving the traces, essentially, at least if p is larger than 2 maybe, determines this representation. Yes, I can tell what the determinant is. I mean, I would have to introduce the canonical operators for this, and it would also match up. So in my paper, I really identify the characteristic polynomials of Frobenius in general. The theorem somehow tells us that these Hecker eigenvalues, which you get from this hyperbolic 3 manifold, see information about Galois representations, although a priori the situation has no connection. And so, yes, so I should say that this should be considered as a mod p version of one direction of the Langlands conjectures. So if you would consider homology of this guy with complex coefficients, then what you would see are certain automorphic representations of GL2 over this imaginary quadratic field. And for those, it was proved by Harris, Lund, Taylor, and Soren recently that you have the attached Galois representations. And so if it so happens that this class mod p lifts to a characteristic 0 class, then one can get these Galois representations simply by reducing their Galois representations mod p. And so my theorem is somehow about the case where this is somehow an actual torsion class, so it does not lift to characteristic 0. So because there exist very big sporadic primes for which there is some actual torsion, this means that there are also this gives examples of very large sporadic Galois representations which are unramified at only a few primes. Some are really about certain sporadic phenomena. And so I should use this Blackbird. In the rest of today's lecture, I want to just give an example of what this means. So the concrete Hecker eigenvalue system and the concrete Galois representation attached to it. And so I took the example from the thesis of Figueiredo. And so in this example, I'm considering mod 3 homology, so P is 3. And I identify the field with 3 elements with 0 and plus minus 1. And I look at the following congruent subgroup. Gamma is gamma 1 at 3 intersected with gamma naught at 61. So it's those gamma such that gamma is congruent to star star 0, 1 mod 3 and congruent to star star 0 star mod 61. So I allow ramification at 2 primes, 3 and 61. Well, actually 61 should be regarded as 2 primes because it's factors as product of 2 primes in this imaginary quadratic field. And I will also use that this is contained in a slightly larger group, which is gamma naught 3 intersected gamma naught 61. Hope you can guess what this means. And so this is a normal subgroup. And the quotient is just given by this diagonal element here. So it's just F3 cross. And I will denote the identity character to F3 cross by chi. Okay, and so I will look at the following homology group. So I will look at the H1, H3 modulo this congruent subgroup gamma with coefficients in F3. And acting on it, because gamma is normal and gamma tilde, I have this quotient gamma tilde over gamma. And so I take the eigenspace for this character chi. And that's also called fixing the Nebentypus. So takes a part of Nebentypus chi. And so this guy will have dimension 2 over F3. And there are two eigenvalue systems alpha 1 and alpha 2. And so you can just go about computing them. And I will tell you the result. Oops. Okay, so what does this blackboard mean? So for any prime which does not divide the level, which is 3 and 61, and this, I'm working mod 3, so 3 is already there. For each such prime, I can look at the Hecke operator TP. And the corresponding Hecke eigenvalues are denoted here for alpha 1 and alpha 2. And I've written in the same line those primes which have the same norm. And it's not a priori clear that they will have the same Hecke eigenvalue. But they do in this case, in all these examples somehow. And to save space, I've denoted them in the same line. So we can make a couple of observations about these numbers. So the first thing is what I just said, that if I have two primes which have the same norm, so the norm is just the square of the absolute value in this case, then they will have the same eigenvalue. So that alpha I p is always equal to alpha I p bar, where I is either 1 or 2. And then there's another thing that happens, namely alpha 1 seems to be 0 exactly when alpha 2 is 0. Okay, so I guess I'll use this blackboard for a moment. Or maybe I shouldn't. Maybe I should just use this blackboard. Okay, so what does the theorem tell us? So the theorem implies that there should exist somewhere representations rho I, rho 1, and rho 2 of the absolute Galois group with values in GL2 F3. A priori in GL2 F3 bar, but because it appears that, well, in this case it's actually true that all these alphas will lie in F3, so the trace is always in the subfield F3, and this implies that also the representation is defined over F3 already. So we get representations actually into GL2F3. As Delim was asking, I can identify the determinant of this representation. And because I fixed this Nebentypus, actually the determinant of these representations will be trivial. So this is because of Nebentypus chi. So actually, they are mappings to SL2F3. And they are unramified outside 3 and 61. And which have this property for the Frobenius eigenvalues. Let's make the following remark. If chi3 is a mod 3 cyclotomic character, so this is simply measuring the action on the two non-trivial third suits of unity. This is ramified only at 3. And this means that if I twist my representation rho 1 with this character, it will still have all the properties that it should have. And so one might ask whether actually the second representation is just this twist of the first representation by chi3. And in this dictionary, this would mean that alpha 1 times chi3 of a Frobenius element should be the same as alpha 2 at P. And so let's write down what chi3 of a Frobenius element would be. And by the way, that's like quadratic reciprocity. This is 1 if the norm of P is 1 mod 3, and minus 1 if the norm of P is 2 mod 3. So it's easy to compute. And it turns out that it works out. Minus 1. Then here it should be minus 1 again, I hope, yes. Then here we have a 0. We don't really know what to expect, but anyway. But at all points, at all data points where there should be some correlation, it works out. So this seems to be actually true. And actually, this relation is something you can actually prove by hand, even if you wouldn't know. I mean, this relation that alpha 1 is equal to this relation here with this formula, something you can actually just prove directly without knowing the existence of the Galois representations. Okay, but let's try to figure out actually what's this. So as these differ just by a twist, we can somehow now concentrate on rho 1 and ask what rho 1 actually is. So move on page. So concentrate on. So I recall that this is a map from the absolute Galois group of K to SL2F3. And actually SL2F3 is, it has, well, I don't remember how many elements, but quite a few. So let's rather look at the reduction rho bar which goes to PSL2 F3. And now that's just a well-known group. It's just the alternating group on 4 elements. And so what does this correspond to? So under this Galois theory correspondence, this corresponds to a degree 4 extension. I called it L rho bar over K, unramified outside 3 and 61, such that its Galois closure will have Galois group A4. And so that's given by some degree 4 polynomial. It's called P of x. Where the AIs so you get this extension L rho bar by joining a root of some the roots of a root of some degree 4 polynomial. And so what we know is a strange relation between the trace of this representation evaluated at Frobenius elements and these alpha p's. And so the following lemma gives a concrete consequence of this. So the following are equivalent. In some sense, P has reduced form. Which means that no extra primes divide the discriminant of this particular polynomial. The first is that P has a root mod P. So there exists some x in the adjoint I such that P of x is maybe not 0, but it's 0 mod P. By the definition of Frobenius elements, one sees easily that this is equivalent to the Frobenius as an element in A4 having a fixed point on 1, 2, 3, 4. So the action of Frobenius describes how mod P, the P's power, will act on these 4 roots of this polynomial, and that it has a fixed point means that there is one which is actually defined over the base field. Then it's an easy exercise in making this isomorphism explicit that this means that the Frobenius element as an element in PSL2F3 is a unipotent element. And this is finally equivalent to a property as we want. So this is equivalent to the trace of Frob P considered as an element in SL2F3. Or the trace, I should say, of this rho of Frob P being plus or minus 1. So we get the following corollary, that there exists some polynomial such that alpha 1p, say, is non-zero if and only if p has a root mod p. Okay, so this means that the strange behavior of when this is 0 or 1 is somewhat the same strange behavior as some polynomial having a root modulus is prime ideal. And in fact, one can make a guess for what this polynomial should be. There exists a unique degree 4 extension L of Q, unramified outside 3 and 61, and whose Galois closure has Galois group A4. And that corresponds to the polynomial x to the 4 minus 7x squared minus 3x plus 1. And so it might be that this field we're interested in is actually just a compositum of this with this field K. This would also explain the strange property that this didn't see whether we take P or P bar, because actually the representation is already defined of a Q. And so now we can numerically test here. Test this relation. So we look at this polynomial mod P, and we find that, so in this case, alpha 1 is non-zero, so we expect that it has a root, and indeed, it factors as a linear polynomial and cubic polynomial. In the second case, again, alpha is non-zero, so we expect that there is a root, and indeed, there is a root. And continues like this. So in this case, x equal to 6 will be a solution. In the next case, x equal to 2 is a solution. Then x equal to 8 is a solution. Then there is no solution. Again, there is no solution. And x is equal to minus 3, and then again, no solution. Okay. So, I mean, even in the examples, like this example of Figueredo, where one had such a concrete polynomial and these concrete Hecke eigenvalues, and see that somehow numerically they matched up, one couldn't prove that there is any relation. One couldn't prove that this is somehow continuous forever, this relationship. Because even if you know what to expect, you couldn't somehow make any relation. Now that we know that there is some Galois representation, somehow checking this, it's just a finite computation. So there are only finitely many possible Galois representations that it might be. Somehow we can rule out one by one until we see, it has to be this one, and then for this one, it actually has to continue forever. So because I'm bad in computer algebra systems, I didn't actually make the check that in this case it's really this polynomial, but it should be okay. And no, I mean, I guess you have to compute further, maybe. I don't know. Well, maybe it's even enough. So, okay. Uh-huh. 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 Yeah. I mean, how far do you have to go roughly? Do you know this? So to end this lecture, I want to make some more remarks on this precise example. I mean, but Figueiredo also writes that he has tested this for like 100 primes or so. I mean, that's only the data that I found in the papers. So this polynomial P that we considered somewhat corresponds actually to, let's call this rho naught. So it's actually defined on the absolute Galois group of Q already, and with values still in SL2 F3. And it is an even representation, which means that the determinant of rho 0 of complex conjugation so I define Q bar as a subfield of C. On C, if complex conjugation, it induces an automorphism of Q bar.
Sorry, I did not understand. You proved that you can lift it.
Yes, you can. I mean, a priori, somehow this P gives only a representation to PSL2F3, and you can check that it actually lifts to SL2F3. Which is an even representation. And so, in this case, if you want, you can even lift this to a complex valued representation, because there's a lift from GL2F3 into GL2C as groups. And so this should conjecturally, well, actually in this case, it's a theorem of, because the group is solvable, it's a theorem of Langland's tunnel. Do I get this right? Well, at least it's a conjecture that it is associated to a certain mass form of eigenvalue a quarter. So to okay, I wasn't sure. Yeah. Yeah. Okay. Sorry. Yeah. I wasn't sure whether it's only a theorem for weight 1 forms. Hmm?
So you can make an example?
You can, I think you can make examples, yes. Okay, let me explain what happens. So there is some kind of automorphic object, which is a non-holomorphic modular form. So these are non-holomorphic forms on this modular curve H2 mod some gamma. But they don't contribute in any way to the homology of the modular curve. So the diagram now is the following. So you have somewhere these mass forms of eigenvalue a quarter. And in general, it is absolutely not known that there exist Galois representation attached to them, which actually should go to SL2C. And these are all even, yes. Okay, no, sorry. It's just representation of GL2C, but it's even. But then you can make the following. So you can restrict this to k. So you get some rho restricted to k. GL to C. And now there's no even-odd distinction anymore because you're over in the imaginary quadratic field, so complex conjugation is not there anymore. And so by Serre's conjecture, you expect that you can go back and find p torsion in the homology of H3 mod gamma where I join some level at p. And that's actually numerically tested. So in precisely such examples. Any p. So you can reduce this representation to GL2 FP bar for any p. And then maybe you have to increase the level at p a bit, but then it should contribute some p torsion in the integral homology. And so no, I don't think so. Gamma p and fp are the same, yes. So it's p torsion in this guy. So there should be some reason. So let me formulate this question. Is there an analytic reason that a mass form on some level gamma n gamma n and eigenvalue a quarter forces p torsion in the first homology of now. So this is on the modular curve, and somehow it should force p torsion on gamma n times p in this group. So this is somehow numerically tested to be true. So somehow there has to be some strange reason that such a mass form, some purely, I don't know, some analytic object, gives rise to torsion suddenly after you went to this imaginary quadratic field. And one doesn't in general expect it to be liftable now. Yeah. This really, yeah, there are examples where this is verified.
I mean, that's already saying that Betty number is not 0 or something.
Well, I mean, the Betty number, yes, might yet be 0, but I mean, there's some torsion in there. I think, yeah. And I mean, if there would be, the answer to this question would be yes, and I think one would have a very good chance of constructing these Galois representation that one expects to mass forms, because if one has these classes in the mod P homology of these arithmetic threefolds, then one, by the theorem, one would get some Galois representations for all P, and then maybe by an argument similarly as in Delign's theorem, one might maybe be able to patch them to the expected even Artin representation.
You don't have any example where you started with a group of non-solvable?
There are examples even for like mod 5 or something.
And in that case, your theorem either doesn't complete this picture. I mean, you're not constructing one case of an Artin L function, even Galois representation, two-dimensional.
No, I mean, I'm not constructing any, no. I mean, even if I say that this has been numerically tested, I mean, I only say that there are hundreds Frobenius eigenvalues which match. Okay. Maybe I stop here today, and the next time I will say something about the proof.